All right, so in this problem, we're going to fold a box up that has two folds to make a solid side here, and then a fold in the middle, and then two more folds to make a solid side there. And what's important to understand that is if I do the length, right, the length of this box, that's a cursive L. It's just better than drawing that, which looks like a 1. The length goes from here to here, and I start with 24 inches. However, each time I make one of these folds, I'm subtracting 1x, 2x's, 3x's, 4x's, and 5x's. And so I'm actually subtracting out 5 folds that become a height. But also, as I'm doing that, right here in the middle, I'm going to have to fold the box in half. So you would also have to divide this by 2. So the width of the box, which goes this direction, I'm going to subtract 1 width here and a second width there. Sorry, 1 height there and a second height there. So the width of the box will be 12 minus 2x. I don't fold that in half. There's no need to fold it across the midline. And the x that we're talking about here actually would form the height. Now I have a cool animation that I found that I'm going to show you. And so watch this picture. Now this one does not have the extra support on the top, so it would be minus 4 divided by 2. But let's take a look at it. You fold those up, that's the width, and then here's the length 1, 2, 3, 4 in this case, and then divided by 2. And that's pretty neat. But mine had 5 to double the strength of this side. And so if I want to find the volume is length times width times height. The volume is this expression. The width is this expression, and the height is this expression. All right, so the next thing we want to do is find the roots, and we're going to find those roots by setting each part equal to 0, which isn't so hard. We've done that before. So if I set this part equal to 0 right here, I'm going to first thing I'm going to do is I'm going to multiply by 2. Then I'm going to subtract 24, right? So after I do that, I subtract 24. And I divide by -5, and I get 4.8. If I set this equal to 0, it's a little easier. I subtract 12, divide by -2, I get 6. And of course, if I set that equal to 0, I get 0. So why did I say the domain restriction was only 0 to 4.8? What about that 6? Let's take a look at a graph of this on Desmos. Okay. If I look at the graph, there it is. I found it. The graph, as you can see, by the way, in my wrench, I changed this from 0 to 200 and then zoomed out. I went from here. I'll actually show you that. I went from 0 to 200, just kind of like a hunch. You could get some more information later in the problem, but I did that to start, and then I just kind of zoomed like that. So what happens is you can see those roots that we found right there: 0, 4.8, and 6. Okay. The problem is that the 6 never actually happens because this represents positive volume. This is negative volume. So how could positive volume yield a negative and then come back to be real world? The problem ends at 4.8. As soon as you get negative volume, the problem is done. So to reinforce that, we're going to go ahead and multiply all this out for standard form. So the way you multiply this out for standard form is you reduce this by making that 24 divided by 2 or 12. You divide the 2 in here and you get -5/2. I also distributed the x in here and got 12x minus 2x squared, which when I multiplied everything together and combined like terms, I got 5x cubed minus 54x squared plus 144x. A notable thing to understand, which is kind of interesting, is how do you think about multiplying that in your head? Most of you would say 12 times -5 is 60. Did you know that you can actually do the 2 into the 12? Let me show you what I mean. 5 times 12 is 60. 60 divided by 2 is -30. But did you know you could take the 2 into the 12 and get 6 and multiply times 5 and still get 30? And you might say, well, that's not easier. What if this 12 was a 26? What's 5 times 26? I have no idea. But 2 into 26 would be 13, and 13 times 5 is 65. That'd be a whole lot easier to do. Just a little interesting thing about fractions in case you didn't know. That's also why you would never write that as a decimal, because 2.5 times 12 means you got to pick up a calculator. But 5/2 you could do in your head. All right, so once you do that, a cool thing to check in Desmos is say to yourself, hey, I wonder if I got that right. So if I were to type in this answer into Desmos and see, notice that I now have a red one for the first thing and a black one for the second thing. Well, if I'm right, that black graph is going to merge with the red graph. Just give me 1 second to finish typing. And as you can see now, you see how it just immediately merged? Okay. So moving forward, I can't really have two of them in there. So the next thing it says is what's the volume of 4? And if I put volume of 4, sorry, volume with the height of 4, not a volume of 4, a volume with the height of 4, it says I don't know which one to use. So I'm going to get rid of the first one now. So the first answer is 32, real easy. But then when I look at the next one, what volume will produce by a height of 5? Once I put 5 in there, I get negative. And that explains why, again, our domain restriction had to be 4.8, because anything over 4.8 gives me a negative volume, and negative volumes don't exist in the real world. Okay, so looking at this next problem, what is the maximum volume? I know that if you had watched my earlier videos about maximums, you probably saw me doing something like negative b over 2a. That doesn't apply because this isn't quadratic, right? This is for quadratics. So for now, we're just going to literally click right there. There's our maximum, right? Our maximum is 1.767, 113. That's what I put right here. It's the output. The input is the height. The output is the volume. That's what V of H means. Why doesn't this matter? Again, it's negative. Negatives don't exist in the real world. The next question is, what is the minimum volume? We already know the answer to that. It's 0, right? Because I can't have anything below 0 because they don't exist. The next question is, hey, let's say Pizza Hut needs your box company to make a new box for their super large pizza, and they want you to use this piece of paper right here that's 24 inches. Let's say they have like 10,000 of these in a warehouse. The question is, could they still use this piece of cardboard to make their new pizza? So the question is, if my maximum was 113 and they want me to do 140, could I do it? And the answer is obviously no. The volume can never be 140 because the maximum is 113. A similar question is, let's say they asked, could it be 120? And the way you would do that, I'm sorry, 120, let's say they said 110. So if I said V of H was 110, the answer is, there are 3 answers. This one doesn't make any sense because it's past the domain restriction, but I would have those 2 options for heights. That would be 110. All right, I hope that was helpful, and I hope you learned something interesting. And these application problems are super important. If you like math,